Okay, a very quick lesson on reactions of ions in solution. So we are going to focus this lesson on something that you've already learned, but we're going to learn some new things about it. Okay, so we are going to take a look at double displacement reactions. Double displacement reactions. And we are going to look at how they are related to solubilities. So, as you may recall, solutes are divided into three categories. Okay, so we have soluble. So instead of solutes, really, we should call these um, ionic compounds. Ionic compounds are divided into three categories. If it is soluble, that means you can dissolve more than 1 gram of it per 100 milliliters. Okay, or 10 grams per liter. Right? Let's show you that that works. Okay, so if we have 1 gram per 100 milliliters, and we know that there are 1,000 milliliters in 1 liter, um, yes, then we have, right? So 1 times 1,000 is 1,000. Okay, divided by 100, divided by 1. And we'll get 10 grams per liter, right? Same amount, we just did a unit conversion on it. Or it could be slightly soluble, which is between 1 and 10 grams per liter. Or it could be insoluble, which has a solubility less than 1 gram per liter. Okay? As you may recall, we have a solubility table. This is from your chemical reactions unit. That's unit 2 in your types of reactions lesson. Okay, so we might refer to this at some point. Maybe I want to take a photo of this. Oh, wait, I can't do that. Hold on 1 second. I have to do screenshots a little bit differently. Device, more, screenshot. There we go. Okay, so that'll be available to me if I need it. And let's go back to the lesson. Okay, so double displacement reaction occurs if two ionic compounds so these are our reactants, react in solution, and they can form either a precipitate, right? So a precipitate is an insoluble compound, or they can form a gas, right? So removed as a gaseous product, or we form water from H plus and OH minus. To determine the solubility rules are used. In general, all family 1 nitrates and ammonium salts are soluble. So if you see, so family 1 would be sodium, lithium, potassium, cesium, francium. I feel like I'm missing an important one. Let's see. What am I missing? Sodium, lithium, potassium, periodic tables, rubidium, our good friend rubidium. Right? All of those are group 1, okay? Or nitrates, which is NO3. So these guys are cations. NO3 minus is an anion. Right? Cations go at the beginning, anions go at the end. Ammonium is NH4. That's another cation. Okay? So expect the group 1 elements and ammonium to be at the beginning, and expect nitrate to be at the end. Okay? I will never expect you to memorize the solubility rules. They'll be on your exam. Don't worry about it. Okay, let's talk about precipitates. Okay, a precipitate is a compound which is formed when an anion and a cation in a solution join together to form an insoluble substance. So, we have our overall equation here. So we have lead nitrate plus potassium iodide, and the cations switch places. Right? And then we get potassium nitrate and lead iodide. And as you can see, we don't have their states filled in, so we can practice looking them up on the solubility table. Okay, KNO3 is made of a group 1 metal and a nitrate. I don't even need to look that up to know that it is soluble. But I will show you. Anyway, I made this blank way too small. AU. There we go. Okay, so I can take a look in my photos, and this is what happens when you teach science. So we needed potassium nitrate. So potassium, you see the group 1 elements. You see how they're all soluble, except for lithium and phosphate. But you can see how they're all soluble. So all of the K pluses, right? You look down, soluble, 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 right? And all of the nitrates, so nitrate is 4th from the bottom, right? There you can see nitrate, NO3 minus, soluble, 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 all the way across, right? So combined, they're definitely soluble. And remember, you just look up where they cross paths, right? And you can see, where's my markup? Oh, it's not letting me mark it up. Oh, edit. That's how we do it. And this one. Right, there we go. Okay, so you can see potassium and nitrate. They're soluble together. What about lead and iodine? So if I go down from lead and I go to where iodine is, you can see it's insoluble, which means that's going to be a precipitate. So, go back to my note. And so this will be a solid, right? So this is the precipitate, PPT for short. Okay, so it says the formation of a precipitate can be determined in advance by checking the solubility tables before writing out the chemical equation, right? If you know which anion and which cation are going to combine, you can just look at the intersection of the anion and the cation in the table, and you can figure out before you write the whole thing whether it will make a precipitate or not. If both products are soluble, no reaction occurs because they're just, it's like you dissolve two things. It's like dissolving salt and a different salt in the same cup. There's no reaction. Okay, so no reaction takes place because all of the ions are still present in solution, and this can be shown by writing NR after the arrow, but not in this one, not in our practice equation. Okay, so I want to talk about different ways that we can represent double displacement reactions now that we're thinking about them in terms of ions. And the first way that we can represent this is a total ionic equation. So this is a chemical equation, right? Everything is in formulas, in which soluble ionic compounds are written in their dissociated form. So this is the same equation as the overall equation, okay? So we look at this, okay? And we break it down into its ions, right? So you can see from the chemical formula in the overall equation, we have one Pb ion, okay? And you can, of course, Pb, is it going to be 2 plus or is it going to be 4 plus? Right? Let's see which one makes the right chemical. Oh, sorry, NO3 is 1 minus. Which one makes the right chemical formula? Right? The 2 plus would make the right chemical formula because it's going, the 2 is going to go and become the nitrate coefficient, just like we have here. Right? So this is Pb2 plus. And then we have 2 NO3 minus, right? This one we can just look up on our, the minus part we can just look up on our reference sheet for polyatomic ions. Okay? So any ionic compound that's aqueous, we're going to turn into ions. 2Ki, we got to turn that into ions, right? Oh, by the way, this one is balanced, right? They don't all come balanced. Okay, so 2Ki, that means I have 2 molecules of Ki, right? So we have Ki, there's the first one. This is the second one. So how many K ions do we have? We have 2. How many I ions do we have? We have 2. Right? Where do I find the charges? Periodic table. Okay, and you'll notice after all of the ions, I put aqueous because ions dissolve in water. Right? So all of your aqueous compounds are going to turn into ions, and all of those ions are going to be aqueous. Okay, KNO3, we decided that was aqueous. So it gets turned into ions, but our precipitate is not aqueous, right? So it's going to stay as a solid. So it says each compound in the reactant is written as ions, since that is their form before a reaction occurs, right? So all of our reactants are going to be in a solution. The precipitate is no longer in ion form, so it is shown as a solid. In other words, we do not break the precipitate up into ions because the whole idea of is it forms and it's insoluble, so it can't break down into ions, right? Once it's joined, it just stays there. That's what a precipitate is. The leftover ions remain written as ions. Okay, so everything that is an aqueous compound gets broken into ions. The precipitate is not an aqueous compound, it stays as is. Then we have the spectator ions. So when you're looking at the total ionic equation, you'll see that some ions appear as ions on both sides, right? So they appear as ions in reactants and products. Right? So they remain unchanged. Okay? So we can see them on both sides of the equation. So let's look at lead. Okay? So lead is Pb2 plus on the reactant side, but on the product side, it's part of the precipitate. These two things are not the same. Okay? So lead is not a spectator ion. Then let's look at NO3. NO3 on the reactant side is an ion, and on the product side is also an ion. So it becomes a spectator ion. Potassium is an ion on the reactant side. It's also an ion on the product side. So it is also a spectator ion. The iodine ends up as a part of the precipitate. It is not a spectator ion. Okay, so we can identify the ions that do react and the ions that don't react. The ions that do react end up in the precipitate. The ions that don't react end up just the same as before, right? So these guys did not react. The word spectator, you might know because we have spectator sports, right? So spectators are the people in the stands, right? They're just watching. They're not playing. Sometimes my dad thinks he plays for the Maple Leafs, but he just yells at the TV, right? So he is a spectator. He did not take part in the hockey game, although he insists otherwise. Did not take part in the reaction here, not the hockey game. In the reaction. Okay? Because the reaction is what forms the precipitate. So the ions that make the precipitate, they're part of the reaction. We can also write something called a net ionic equation. Okay, a net ionic equation is a chemical equation that includes only the entities that took part in the reaction, e.g., the anion and cation in the reactants, which join together to form the precipitate. Right? What is the precipitate? Lead iodide. What made lead iodide? The lead and the iodide. Right? So we can go from the total ionic equation to the net ionic equation by removing the spectator ions. Right? Do you see any NO3 in this equation? No. Do you see any K plus in this equation? No. We removed them because they didn't take part in the equation. So, a summary of steps on how to go from a balanced equation to a net ionic equation. Number 1, write a balanced chemical equation. Sometimes you'll be given a balanced chemical equation. Sometimes you'll be given just the reactants. Sometimes you'll be given the chemical formula. Sometimes you'll be given the names. Okay, we know how to get to a balanced chemical equation because we took the chemical reactions unit. Use the solubility table to determine whether a compound precipitates. Right, so solubility table to determine whether a compound precipitates and indicate the states of the products. Right, if no precipitate forms, you can skip the rest of the steps and write NR. Now, if you do have a precipitate, you are going to write the total ionic equation. How do you write the total ionic equation? By showing all the soluble compounds as ions, right? We're going to dissociate them. And then we are going to identify spectator ions and cancel them because we don't need them in our net ionic equation. Let's practice. Oh, it says note, two precipitates, a gas or water, can also be formed in the reaction. So if we form a gas, we'll also the reaction will also complete, or if we form water, a reaction will also complete. So it says write overall, then ionic, then net ionic equations, as well as stating the spectator ions for each of the following. So it says aqueous solutions of potassium chloride and copper 2 nitrate. So the first thing that we have to do here is we have to go from the words to the chemical formulas. Okay, so potassium chloride, right? We can, I'm going to go up here and I'm going to put, so, oh, hold on. There we go. Okay, so we have potassium and chlorine, and we have copper 1 and nitrate. Okay, so we can use, right? So the K, the Cl, and the K and the Cl, I looked up their charges on the periodic table. The copper, I found its charge in the Roman numeral, and so the periodic table, Roman numeral, reference sheet. Right, that's where you look for the charges. Okay, so using the crisscross rule, we can come up with KCl, right? And it's a reactant, so it's going to be aqueous, plus CuNO3, also aqueous. Then we need our arrow, and now we need to predict the products. Okay, so while we're doing that, so we know the potassium and the copper are going to change places. So we need to look up copper and chlorine and potassium and nitrate. Actually, we don't have to look up potassium and nitrate because we've done those before and we know all group 1 elements are soluble and all nitrate containing compounds are soluble. So this one's going to be aqueous. We're just going to look up the other one. That is copper chloride. Okay, copper chloride. So the intersection of, here's copper and chlorine. Copper and chlorine are, oh, this is copper 2 plus. We need copper 1 plus. We don't have copper 1 plus. That's going to be a problem. Okay, so we need a different solubility table. Well, that's annoying. So hold on while we look this one up. Okay. So we're going to look for a solubility table that has Cu1. Where's my plus? Can I just write the plus in up here? No. Oh, I see. Nope. There. Okay. Okay. Let's look for a nice image. This one. There we go. Okay. So you can see here we have copper plus and we have chlorine, and they make low solubility together. So the positive ion is copper plus. The chloride ion, when you combine them, it's low solubility. So there are hundreds of um, different solubility tables, and can't always get them all. Okay. So yes, copper 1 nitrate is copper 1 chloride is going to be a precipitate. Okay, so that's the overall equation. Is it balanced? Yes, because we have one of everything. So the ionic, we are going to take a look at a compound. If it's aqueous, we are going to break it up into ions. Pretty boring. And you have to write aqueous, and you have to make sure you use the charge. Right, this is copper 1 nitrate. So we're just going to go back to before we uncrossed it. We're going to go back to before we use the crossover rule and just write out everything as an ion. Then our arrow comes. We have K plus, aqueous, because this is an aqueous compound. NO3 minus, which is aqueous. And the precipitate we do not break up, so it just stays as CuCl solid. That is our ionic equation. And to find our net ionic equation, first we have to go hunting for spectator ions. Okay? Same on both sides. This is a spectator ion. Same on both sides. That's a spectator ion. So what is left over should be what the ions that make up the precipitate. So Cl minus Aq plus Du plus Aq makes DuCl solid. And that's our net ionic equation. So this is really pretty easy. Let's try the next one. Aqueous solutions of calcium bromide and ammonium carbonate are mixed. So first we have to find calcium bromide. So we look up calcium on the periodic table. Right, we have Ca2+, and then we have Br bromide minus, and then we have ammonium, which is NH4 plus, and we have carbonate, which is CO3 2 minus. Okay, crossover rule time. Calcium bromide is going to be CaBr2 aqueous plus. This is going to be NH4 2 CO3, also aqueous. Arrow are two products. So calcium is going to go with carbonate, and ammonium is going to go with bromine. Okay, so I know that all ammonium compounds should be soluble, and I don't know about calcium or carbonate. So just to show you, ammonium and bromine make a soluble compound. Then we have calcium and we have carbonate. Calcium carbonate is insoluble. Actually, that's what chalk is made out of, or what it used to be made out of anyway. So, calcium carbonate is going to be our precipitate, and ammonium bromide. Oh, Da. Right, we have to come up with the correct chemical formula. Sorry for skipping that step. So the twos are going to reduce, and we're going to get CaCO3. And then we're going to do the same for ammonium, NH4, that's plus, and Br minus, right? We're going to get an NH4Br. And it's going to be aqueous. Okay, so let's try to write the total ionic equation. So we have, to begin with, Ca2 plus, aqueous, plus 2 Br, right? So this subscript becomes a coefficient, 2 Br minus, aqueous, plus 2 NH4s, which are aqueous, plus CO3 2 minus, which is aqueous, arrow. Don't need to touch calcium carbonate, it's the precipitate. But we do need to break up NH4Br. NH4 plus aqueous plus Br minus aqueous. Woo! My arm is sore. Okay, next identify the spectator ions, the ones that are ions on both sides. So calcium ends up becoming a part of precipitate. We'll leave that. Bromine, though, we didn't balance this. We need a 2 here. Otherwise, the ammoniums won't match up. And neither will the bromine. Okay, now we're fine. So, we have 2 bromines. That's the great thing about coming up with a total ionic equation. If you forgot to balance, you can see that everything, including the coefficient, should be the same on both sides. If they're not, you messed up somewhere and probably didn't balance. Ammonium is also a spectator ion. So when we go to write the net ionic equation, we have Ca2 plus, aqueous, plus CO3 2 minus, aqueous, makes CaCO3 solid, right? So we only have the ions that make up the precipitate. Let's try a third one. It says aqueous solutions of iron 3 nitrate. So iron 3 and nitrate. So this is going to turn into Fe bracket NO3 bracket 3 aqueous plus sodium phosphate. Sodium is Na plus, and phosphate is PO4 3 minus. Crossover rule. we get Na3PO4, also aqueous. Okay, now, when we mix those, we get what? Iron is going to go with phosphate. Let's check it to see if that's the precipitate. Iron is going to go with phosphate. Iron 3 plus is here, and phosphate is down here. And where they meet, we see it's insoluble. And then we have sodium. Is it sodium nitrate? Sodium nitrate. Sodium, remember, all nitrates are soluble, and all group 1s are soluble. So sodium, everything is soluble. And nitrate, everything is soluble, right? So it's going to be soluble, is what I'm trying to tell you. Okay, so this reaction will happen because we have a precipitate. So we have iron iron 3 plus. We have to choose 3 plus this time because it's the most common charge. So we're going to get FePO4. Right, the charges will cancel. It's going to be a solid, and we're going to get Na and NO3. So Na has a charge of +1, NO3 has a charge of -1. So we're just going to get NaNO3 aqueous. Right, you don't have to put the solid one first. You don't have to put the solid one second. Doesn't matter to me. I can read it just fine either way. Okay, is it balanced? No. We need 3 of these. And now it's balanced. Okay, so the total ionic equation, everything aqueous becomes ions. So that means we have Fe3 plus aqueous plus 3NO3 minus aqueous plus 3Na plus aqueous plus PO4 3 minus aqueous arrow. Will I make it? No. We're going to write everything a little bit smaller. Oops. Plus 3Na plus aqueous plus PO4 3 minus aqueous arrow. This is the precipitate, so we just write it as is, FePO4 solid plus 3Na plus aqueous plus NO3 minus aqueous. Okay, check that everything. Oh, there's 3 of them. Drat. Plus 3NO3 minus aqueous. Okay, so now we look for spectator ions. Okay, the Fe becomes part of the precipitate. The NO3 does not. The Na does not. And then everything else needs to be there. So Fe3 plus aqueous plus PO4 3 minus aqueous makes FePO4 solid That's the net ionic equation. We have homework. I'm just going to do the homework on the same video. It's only 5 questions. So you can pause here, try the homework, and then come back and take a look. So our first question is they've come up with the overall reaction. It reacts because something is solid there. So for question 1, we need to come up with the ionic equation, right? So everything that is aqueous, right? These 3 things will get turned into ions. The AgCl will not. So silver has a charge of 1 plus from the periodic table. NO3 has a charge of 1 minus from the reference sheet for polyatomic ions. Plus, K has a charge of 1 plus from the periodic table. Cl has a charge of 1 minus from the periodic table. Arrow. AgCl stays as it is because it's the precipitate. Potassium has a charge of 1 plus, and nitrate has a charge of 1 minus. Okay, then we need to come up with the net. Before we come up with the net, we need to see what ions are part of the precipitate and what are not. Silver is part of the precipitate. Nitrate is not. Potassium is not. Chlorine is. So we have our net ionic equation. We have Ag plus AQ plus Cl minus AQ makes AgCl solid. Done. Oh, that wasn't question 2. Okay, question 2. We are given an equation. This one does not appear to be balanced. We have 2 sodiums on the left-hand side, but only 1 on the right-hand side. And we have 2 nitrates on the left-hand side. And now we have 2. I put the coefficient there on the right-hand side. 1 carbonate on both sides, 1 magnesium on both sides. Now we're ready to go. So here we had to do the extra step of balancing our overall equation. Let's come up with an ionic equation, a total ionic equation. So anything that is aqueous gets turned into ions. So we have Mg2 plus aqueous plus 2NO3 minus aqueous plus 2Na plus aqueous plus CO3 2 minus aqueous arrow. Then we have MgCO3 solid because it's the precipitate plus 2Na plus aqueous plus 2NO3 minus aqueous. Okay, find the spectator ions. Mg becomes part of the precipitate. 2NO3 minus is an ion on both sides, and 2Na plus is an ion on both sides. So those are our spectator ions, and we're not going to include those in the net ionic equation. So we have Mg2 plus aqueous plus DO3, 2 minus aqueous, becomes MgDO3 solid. Easy peasy. 3 is a little bit harder. We're going to have to come up with some chemical formulas. We're going to have to do a little crisscross rule. Right? Strontium is Sr. Strontium is 2 plus. Have to think about that for a second. So we have Sr2 plus and Br minus. Here we have, actually, let me see if I can. I'm thinking about something. Okay. So we have potassium, which is K plus, sulfate, which is SO4 2 minus. We have strontium sulfate, which is Sr2 plus, and SO4 2 minus. And then we have potassium bromide. Okay, so let's do all three here. So overall, we have, I'm going to try to leave a space at the beginning of each compound for a coefficient, just in case we need to balance. So we have, overall, we have SRBr2 aqueous plus, leave a space, K2SO4 aqueous makes SrSO4 aqueous plus KBr. Oh wait, sorry. SrSO4 is solid because it's the precipitate. Okay, is this balanced? No. I will need to put a 2 here to balance. Ionic. Okay, everything that is aqueous becomes an ion. So we have Sr2 plus aqueous plus 2Br minus aqueous plus 2K plus aqueous plus SO4 2 minus aqueous arrow SrSO4 solid plus 2K plus aqueous plus 2Br minus aqueous. Whew. Okay, and then we're going to identify the spectator ions, the ones that don't become the precipitate. Strontium becomes part of the precipitate, bromine does not, and potassium does not. So our net ionic equation is going to be Sr2 plus aqueous plus SO4 2 minus aqueous makes SrSO4 solid. Okay. Our next two, I feel like we only have room for the ionic in that equation. I'm going to, so we sort of did the steps of how to do number 3 as coming up with a chemical formula, so I'm gonna sort of do the same. Manganese 2 chloride is MnCl2 aqueous plus ammonium carbonate. Ammonium is NH4. Carbonate is CO3 with a 2 minus. So NH4 has a 1 plus charge. CO3 has a 2 minus charge. So it's going to be this. Arrow, manganese 2 carbonate, which is solid. So these both have a charge of 2. So this is just going to be MnCO3. And this last one will be NH4 Cl. And it's going to be aqueous. So, looking at my balancing, I'm going to need a 2 here. Okay, so this is the overall. Okay, for 4, the total ionic equation was I thinking? The ionic equation, or the total ionic equation, is going to be Mn2 plus Aq plus 2Cl minus Aq plus 2NH4 positive Aq plus CO3 2 minus Aq. Now we have an arrow, and then we have MnCO3, which is a solid because it's a precipitate, plus 2NH4 plus aqueous, and plus 2Cl minus aqueous. Okay, and then before we do our nets, we're going to figure out which ones are our spectator ions. So manganese becomes part of the precipitate. Chlorine does not, and ammonium does not. So our net ionic equation is Mn2 plus aqueous plus CO3 2 minus aqueous makes MnCO3 solid. Okay, this last one I'm going to do in red up here so we don't confuse it with anything else. So chromium 3 nitrate is going to be CrNO3 3. Iron 2 sulfate is going to be FeSO4 AQ. Chromium 3 sulfate is going to be Cr2SO4 3 aqueous, plus iron 2 nitrate is going to be FeNO3 2 aqueous. Is this thing balanced? It is not. So let's start with metals. Chromium is a metal. Looks like this needs a 2. And then that balances. And then iron is also a metal. It is balanced for now. Okay. Now let's look at nitrate. Nitrate, there's 6 on the left-hand side, and there is, needs to be a 3 there, which means we unbalanced iron, so there's got to be a 3 there, and now everything is balanced. Okay, so question 5. We're going to come up with the ionic. This is going to be a doozy. Gotta already do my smallest rating. So our ionic. Okay, we have 3 plus, right? Because it is, after all, chromium. Whoa. Okay, 2Cr3 plus aqueous plus 3NO3 minus aqueous plus 3Fe2 plus aqueous plus SO4, 3SO4 minus aqueous arrow Cr2SO4 solid plus 3Fe2 plus aqueous plus 6NO3. Oh, I read this wrong. Okay, so you see how I put the 3NO3 there? That's because I looked at this. But I also have to consider this 2 coefficient. 2 times 3 gives me, instead of 3, well, this is going to be a big eraser. There we go. Right? I'm going to need 6. And then over here in Fe 3FeNO32, I also have 6NO3 minus AQ. Okay, now everything is going to work out. So, spectator ions time. The chromium is part of the precipitate. The nitrate is not. And the iron is not. So our net ionic equation is going to be 2Br3 plus AQ plus 3SO4 2 minus AQ. Arrow Cr2 bracket SO4 bracket 3 solid. And that's how you write total ionic and net ionic equations.